Let's continue with chapter 22. We just finished Faraday's law that told us there was an EMF and a current induced in a loop when the flux through it was changing. So now we can use Lenz's law to figure out what's the direction of that current that's induced in the loop. So Lenz's law does not have an equation, so we just have to go through these steps to figure out which way is the induced current. So I have these examples done in the review, and we've done these several times. So I'll just show one case of each. So let's say you have a magnet, and let's say the magnet is coming from below this time. This is your loop. And so you need to know that the magnetic field is pointing up here through the loop, because the magnetic field always points up away from the north towards the south. Right there, it forms a loop here. We don't care about the loop, we just care that it's going up through this loop. And that's the first question, which way is the field going? So you can say, okay, the field is going up. Is the flux through the loop increasing or decreasing? Well, the magnet is getting closer. That means the flux is increasing. And then that means that the induced current is going to produce a magnetic field in the opposite direction of the original field. So the induced current in here is going to want to produce a field downward. So that means that your fingers have to loop this way. So as viewed from above, that would be clockwise. So let's do one more. Let's do a motional EMF example. So we've got our bar, and we have our external field, let's say, is moving this way. Sorry, it's not moving. The field is going into the page. And let's say that the bar is moving to the left. So the flux through this loop is decreasing. So we know that we can use Lenz's law here. So what's the original direction of the magnetic field? B was into the page. Is the flux increasing or decreasing? Well, when the bar moves to the left, the area of this loop gets smaller. So the flux is decreasing. So that means that the induced current is now going to produce a field in the same direction of the original field. So now the current here is going to produce a field into the page. So that means this is going to loop clockwise. So your fingers curl clockwise and the thumb is into the page. And then the next thing here, this is a conceptual thing, is what's the difference between motors and generators. So motors convert electrical energy to mechanical energy. Now you don't just want to memorize that motors is electrical to mechanical and generators is mechanical to electrical. You want to be able to visualize what is happening in each one. So what you have for the motor is that the current is provided, right? You have a loop and there's already some current. That means there's got to be some battery, some source of power. The current is provided. That's the electrical energy, right? The current is provided, and as a result, you have this external field here. So you've got this big north pole of this side and the south pole over on this side. So you've got this external field, and as a result of the input's electrical energy, you're going to have that rotation. You're going to have that torque. So that's what's happening. You're getting the electricity and you're getting rotation out of it. You're getting a force that rotates your loop out of it. Now the generator is the opposite. In the generator, you are physically rotating this loop with your hand, with the water, with whatever. You are providing the torque, the mechanical energy. And there is that external field again. And so the flux through the loop is changing. There's going to be a current that is induced one way or the other in this loop here. So you're getting the current out by providing that rotation. So you really need to be able to visualize each process, not just memorize what it says here.